Vector functions are a way to represent curves that are on the plane or in space. When we talk about space curves, what we mean is in R3. Before introducing vector functions, I want to remind us of what real valued functions look like. A real valued function takes in a single real number, and that number goes into the function. We often use this kind of machine diagram. Say it's a box and it spits out a y value when you give it an x value, and y is equal to f of x. In the case of a real valued function, our input is a real number or a scalar. The output is a real number or a scalar. In the case of a vector function, the input is still a real number or a scalar. The function itself is a vector and so has vector notation. The output is a vector, say r of t, and this is a key difference between a real valued function and a vector valued function. The inputs resemble each other, the outputs do not. In R3, a vector function can be represented as r of t is equal to f of t, g of t, h of t, the components of which are each functions. I've used the angle bracket notation here, but we could just as accurately represent it using I, j, and k. So f of t I plus g of t j plus h of t k. You may recall that we already saw something like this when we looked at lines in space. And just with lines, the vector functions can be represented parametrically. We would say that x is equal to f of t, y is equal to g of t, z is equal to h of t. And just with lines, the curve that is traced out by a vector function is traced out by the heads of vectors. So suppose we have a curve in space, and I'll just give you a trace in the xy plane so you can just kind of get a sense of how it might look. I don't like how I did the tail here. Give me just a minute. There, that looks more plausible. So this curve here, it's a curve, we might call it C, but it's r of t, the vector function. And the idea is that for any particular value of t, we have a vector that in standard position, its tail is at the origin, and its head will be a point on the curve. The vector itself is the vector f of t, g of t, h of t, but the point on the curve is x, y, z, where x is f of t, y is g of t, z is h of t. And as t goes through values of real numbers, we end up with various vectors that trace out the path of the curve. And one way to think of it is it's kind of like a laser pointer. If a laser pointer had a finite range, then its tip might trace out a curve in space, much like this vector representation is doing. Actually, rather than trying to imagine that a laser pointer has a finite range, if there were a room that had smoke kind of just clouding in the sky here, and you pointed a laser up at the smoke, what you would see is the laser interacting with the smoke, and as that laser moves around, that tip would be tracing a curve in the smoke. That's probably a better representation. Now let's get away from lasers and smoke and let's talk about limits. Limits work exactly how you would expect. The limit as t approaches a of r of t is going to be the limit as t approaches a of f of t, the limit as t approaches a of g of t, and the limit as t approaches a of h of t. In other words, we find the limits of the components individually, put them together as a vector at the end, provided the limits exist, and that'll be the limit of the function. Just as limits work the way you would expect, continuity works the way we would expect as well. The vector function r is continuous at a if the limit as t approaches a of r of t is the function value r of a. Well, one of the first things that we do when we consider functions is we start talking about their domains. And we're going to find the domain of r of t is equal to the cosine of ti plus the natural log of tj plus 1 over t minus 2k. We're going to consider the component functions individually, but any value of t has to go into all of them simultaneously. For the cosine of t, t can be any real number, so that doesn't give us any restrictions. For the natural log of t, the domain of the natural log is that t has to be greater than 0. And for 1 over t minus 2, of course, t cannot equal 2. Now, I have not written down the domain. These are really just notes for myself. A way to visualize what's going on here is to picture a number line. We'll mark it t. And I'll put a couple of values on here, 0 and 2, because those are points of interest for the domains that we were looking at. Because t can't equal 2, we need, I'll use parentheses there at 2. And we can be anything else for the k component function. For the natural log, we saw that t has to be greater than 0. And so again, an open parenthesis at 0 opening to the right. And then for the cosine function, t can be any real number. Our domain is any portion that has all three colors, of course. So in this case, the domain is going to be the interval from 0 to 2 together with the interval from 2 to infinity. This can be written in set builder notation by saying it's the set of t that are in the real numbers such that t is greater than 0 and t does not equal 2. Either of these is acceptable as a final answer as far as I'm concerned. Now let's consider a limit. We're going to find the limit as t approaches 1 of t squared minus t over t minus 1, I, plus the square root of t plus 8, j, plus the sine of pi t divided by the natural log of t, k. We're again going to take these component by component, and I'm first going to look at the limit as t approaches 1 of t squared minus t over t minus 1. We can see we have an indeterminate form, but in the numerator t factors out into t minus 1. In the denominator we have t minus 1, so those divide out. This limit's going to turn out to be 1. On to the next. As t approaches 1, the limit of the square root of t plus 8 is equal to the square root of 9, and so 3. We've been able to make quick work of the first two. Let's see how the last one goes. We're looking at the limit as t approaches 1 of the sine of pi t divided by the natural log of t. And I again see that we have an indeterminate form here. 0 in the numerator, 0 in the denominator. This time, a simple algebraic simplification isn't going to work, but L'Hopital's rule will. And so we're looking at the limit as t approaches 1 of pi times the cosine of pi t in the numerator and 1 over t in the denominator. At this point, direct substitution will yield that the limit is negative pi because we have pi in the numerator, cosine of pi is negative 1. In the denominator, 1 over t as t approaches 1 is 1. So the limit here is equal to the vector I plus 3j minus pi k. And that's what's meant by limits work the way you think they would.